Hi, chemistry. We're going to talk today about another conversion factor called molar volume. But before we can talk about molar volume, we really need to revisit the states of matter. So I'm going to play a little FET for you. Now, I'll give you the link to this FET, and you can play with the FET as well. It walks you through how atoms and molecules behave in the different states. So as you're watching this FET, I really want you to look for differences in two things: spacing and movement. Okay, so here is the FET that we're looking at. Notice up here you can play with atoms and molecules. We can switch between neon, argon, oxygen, and water. So notice that our temperature right now is around 146 Kelvin, which is not very warm. It's around, negative 127 degrees Celsius. So it's pretty cold. And so all of the things we're dealing with are going to be in the solid state. So notice here's water in the solid state. Definite crystal arrangement, but the molecules still have movement. When we are looking on the molecular level, temperature really denotes whether energy is moving in or out of a system. And when we talk about energy in a system, we're talking about movement. So every time you hear me talk about a temperature, I want you to think movement, right? So at a very low temperature like we're going to have a low amount of movement, but movement is still occurring. We can see the solid shape of water, the solid shape of oxygen. Again, a very ordered, very crystalline type of a structure, but there's still movement of the molecules inside of it. Same thing for argon. Very ordered, crystalline structure, still movement inside it. Same thing with neon. So we're going to add a little heat to this system, and we're going to see this transition between solid states, like we've seen, very closely packed, usually, where we have molecules vibrating in it. We're going to see it transition to a liquid state. So let's do it for neon first. We're going to add a little bit of heat. And you can see it starts to separate a little bit. So a couple pieces have broken off and become gaseous, but the bulk of our neon is still there. Notice that there's some attraction between molecules, keeping it as a body together, right? But there's more movement. So we added a little bit of temperature. Now there's more movement in our system. Along with more movement comes a little bit more spacing. Same thing with argon, a little bit more temperature, gives it a little bit more movement. These molecules bounce off of each other a little bit harder. There's a little bit more space, but mostly they're still attracted to each other here. And they're moving as a body, as a fluid, right? Like a liquid would. You can see oxygen is the same. It's not quite that crystalline structure anymore, but there's not a whole lot of movement there. Water, there's definitely more movement, more spacing. Actually, water is an interesting case because it expands as a solid. So there's actually less spacing for water, but water is definitely an exception there. Most things will have a little bit more spacing, a little bit more movement in the liquid form. Okay, let's add a little bit more. We'll go back to neon, add a little bit more heat, and watch what happens in the gaseous phase. And the gas phase is really what we're going to talk about today. So let's add enough heat to get all of these things separated. So notice that as we add heat, the movement increases. The molecules interact less with each other. We don't really have a body of fluid anymore. Just take that away. That's moving all together inside this container. We really see individual atoms here moving on their own. So gas phase, lots of space, lots of movement. The molecules move independently of one another. Same thing can be said for argon. Now, there's a little bit more interaction with oxygen, and so it has a tendency to these molecules have a tendency to interact a little bit more in order to get them out of this liquid phase where they're sliding past one another, still attracted to each other, into a gas phase. We might need to add a little bit more heat. Add a little bit more heat, add a little bit more movement, and that movement can really overcome these interactions. A lot more heat. There we go. Molecules are starting to move faster, starting to interact less, and starting to move a little bit more independently of one another. And you can see as they bounce off of each other, they really don't stick anymore. So their movement, their kinetic energy, their movement overcomes that interaction they might feel towards one another. And they move more independently. And even with water, we see that water has this really strong polarity, has this really strong attraction to each other. So even with water, the more heat we add, the more these water molecules are going to bounce off each other. That movement of the water molecules is going to overcome the attraction that they feel for each other. And even in water, we're going to get these collisions that happen without the sticking. The molecules are moving independently. Okay, so this state, the gas state, is very unique compared to the other two states. And that's where we're going to land today. We're going to talk about molar volume. And molar volume really only pertains to a gaseous state. Because as you look at the liquids and the solids in this PhET, in this simulation, you can see that liquids and solids tend to attract, they tend to condense, and they tend to order each other. And so the liquids and solids are going to have their own unique volume. But gases don't. Look at the gases for neon, argon, oxygen, and water. They all take up the same amount of space. Neon takes up the whole container. Argon gas, whole container. Oxygen gas takes up the whole container. Water gas takes up the whole container, right? And so, I don't know why my heat dropped on this one. The volume of any gas is going to be very, very similar, and it doesn't matter what makes that gas up. Gases tend to move very fast. They have a lot of motion, a lot of movement. They're bouncing off each other. They're not sticking very much, very little interaction. And so gases tend to spread themselves out very similarly, whether they're made out of something very nonpolar like neon that doesn't have a strong attraction for other neon atoms, or whether they're made out of something that has a very strong attraction, like water. Water's very attracted to other water molecules. But when you get into this gaseous phase, they all spread out, and they're moving fast enough that they can bounce off each other with very little interaction. And they're going to space each other out, and they're going to be so far away from other molecules that they're not close enough to feel the attraction anyway. And so gases all tend to have very similar volumes. This is takeaway number one. Gases tend to have very similar volumes no matter what that gas is. Now, that statement's not true for liquids and solids. It's really only true for gases, and we can reset this PhET back down to this very low temperature, 14 degrees Kelvin. Very, very, very cold. 273 degrees Kelvin is 0 degrees Celsius. So it's very cold. And you'll notice that the solid size and shape tend to be different. Same is true for liquids. If we heat up water until it becomes a liquid, right, it has a very unique volume. If we heat up oxygen until it's a liquid, it has a different volume. Argon has a different volume. Neon has a different volume. So the volume of solids, very unique to the compound or to the molecule, to the atom. Liquids, the volume's very unique to that substance, but gases all have very similar volumes. Okay, so that brings us back to molar volume. Because gases have very similar volumes, no matter what the gas is made out of, a mole of a gas will have a very consistent volume. So at STP, for a gas, no matter the substance, 1 mole of that gas is going to take up about 22.4 liters. And that, my friends, is a molar volume. Again, this is not true for liquids, not true for solids. The difference in attraction between various liquids, various solids, will give it a very unique volume. But for gases, there's just so much movement. Their collisions are so strong, they overcome any interaction. Gases tend to be very far away from each other, where they can't actually attract the next gas molecule. And so gases have a very consistent volume no matter what that gas is, whether it's polar, nonpolar, it's an atom, it's a molecule, it doesn't matter. It has a very consistent gas. Now, this is a very specific quantity. It's only true at STP. Now, STP is standard temperature and pressure. So that's about room temp. If you lower the temperature, this is not going to be true. If you raise the temperature wildly, this won't be true. So it's only true at STP, which is around room temperature. And it's only true for a gas. It's not true for liquids. It's not true for solids. But as long as you have a gas at STP, you have another conversion factor, right? You can now convert between moles of a gas and liters of a gas. We can write this equivalent statement as a fraction. 1 mole of a gas over 22.4 liters. Or if you're trying to convert the other way, 22.4 liters over 1 mole of gas. All right, so if you are keeping 3x5 cards and turning them into conversion factors, definitely put this one on. It gives you a really convenient path to convert between moles and liters. And as we've seen, moles can lead to a lot of other things. Moles can lead to particles. Moles can lead to mass. Well, here we have moles leading to liters. So write this down. Let me know what questions you have. We're going to practice this together. I'll see you in class.